Thanks for the introduction. Welcome from my side as well. So this talk is basically an application of secure multi-party computation. And if I would have to define MPC with just one sentence, it would be it allows multiple parties to compute a function on their combined private input without leaking these inputs to each other. But it's actually a very flexible technology with tons of different protocols optimized for a lot of different use cases, different trust assumptions, different security models. And most notably, we have the semi-honest security model, which is considered secure as long as the parties follow the protocol honestly. And we have the malicious security model where the parties can detect other parties deviating from the protocol. So similar to homomorphic encryption and zero knowledge, this technology can therefore be applied to tons of different use cases to gain some privacy. So we've heard today already about privacy-preserving machine learning. We had threshold decryption in homomorphic encryption. Threshold signatures are another use cases in threshold wallets. And in this project, we're actually applying it for decentralization purposes. And we are going to decentralize a part of the World ID infrastructure of the World Coin Foundation. So what is World ID? So it's basically an attempt to bring a unique identifier for each person to the internet. So when you sign up, you get a unique identifier, and then you can use that to authenticate yourself to other services on the internet. And you can also do this authentication via zero knowledge proofs, for example. But this is not the part we are going to interested in this talk. So when you want to sign up for this World ID infrastructure, what you get from WorldCoin is actually that this is a proof of personhood. So basically, they want to give an ID only to humans, and it should also not be possible for humans to sign up twice. So if I already have an ID and I want to sign up again, I should get rejected. So this should also prevent some AI models which will come in the future to authenticate themselves to different services on the internet. So if you only want to authenticate for specific humans, they decided that it's the best way to do it via some biometric information. So when you want to sign up, you go to a station where some WorldCoin orb is located. It gets a scan of your iris, sends it to a database hosted by WorldCoin, and then it checks whether your iris was also already be used for the sign up for this World ID. And if this iris was already located in a database, then you should get rejected. So that basically means there is somewhere a server with a database full of iris codes. So there is this database is currently hosted by WorldCoin Foundation, and this can have some huge privacy implications. So this is a database full of biometric information, so this has a lot of privacy concerns, but on the other hand, it can also be used for some misuse. For example, they could try to recreate a picture of the iris code, authenticate for different service. It's a single point of failure. The database could be stolen by some malicious party, which could also try to misuse this database. And also, if I'm this server here having this database, I could also try to censor some people and preventing the people from signing up to the service. So having one single database server is definitely not the best solution for this protocol. But luckily, we can use MPC to decentralize this database. So we envision it, it looks like the following. Instead of having one server with the full database which basically computes the protocol, we secret share this database among multiple servers. In our use case, it would be 3 servers. So we decentralize this with MPC. And this basically means that each of these servers has access to some random data. So from their point of view, it's fully random. But if they would combine these shares, they could reconstruct the original database. And also, when we have a new sign up at the orb station, this orb does not send this iris code in plain to the servers, but it also secret shares it amongst these the 3 computing servers. So that basically means that none of these servers has access to the database on its own, and none of these servers actually learns the new iris code that gets authenticated. But with MPC, we can actually still compute whether this new iris code is actually located in the database or not. But of course, this sounds very good, but similar to homomorphic encryption and zero knowledge, applying MPC to this use case adds some overhead to the computation. And this overhead is in MPC, the most significant cost factor is usually the communication between these free computing parties here, when they compute this protocol, they have to exchange randomized data, and this is usually considered the main bottleneck in MPC applications. And the concrete bottleneck depends on the protocol that is executed. So now let's have a look what has to be done when we compare an iris code to this database. So currently the database for WorldCoin has about 3 million iris codes, and each iris code is basically a bit string consisting of 12,800 bits. And when I send a new iris code, since this is basically constructed from an image of your iris, you cannot just directly compare each iris code in the database to the new iris, so say these are equal or not. So because these images, of course, can have some bit mistakes. So what you're doing in practice is you calculate the Hamming distance between the new iris and each iris code in the database. And if the Hamming distance is smaller than a threshold, you consider this as being 2 equal iris codes. And the Hamming distance is usually just calculated as the X operation between the new iris code and the iris code from the database, and then you count how many bits are set. So this sounds like a very simple protocol, but unfortunately, when we translate this to MPC, it's not. It has some pitfalls where you can say this can become very inefficient. So the first pitfall is actually that it is a protocol full of mixed operations. So the Hamming distance, first you have to compute the X operations, which is a Boolean operation, and then you have to sum up how many bits are set in the result. And you get as a result a larger integer. In our case, it will be a 16-bit integer. And then finally, when you want to compare this Hamming distance to a threshold, this is usually also done by evaluating a binary circuit. And so mixing Boolean operations with integer operations is usually considered something that can be very inefficient in these MPC protocols. And the second point of problem in MPC is also this communication overhead that I mentioned. In secret sharing based MPC, these parties have to communicate randomized data for each multiplication and AND gate, and this can be a problem when the database is pretty huge. So we said we had about 3 million iris codes in the database, and when we just compute this protocol here as a binary circuit, then the communication gets pretty large. So for a database of just 1 million iris codes, the parties already have to communicate about 3 gigabytes of data, and this, depending on the network, can already last, can take several seconds, and this can be a huge bottleneck for practical application. So we have to carefully design an MPC protocol to reduce this communication to actually make it practical. So now let's talk about our proposed solution for this protocol. And first I want to talk about the efficient Hamming distance calculation, because the Hamming distance is actually where most of this 3 gigabyte communication comes. So what we did when we looked at this protocol was the first thing what we did was rewriting the Hamming distance computation from the XOR and the sum to this expression here. So we basically, when A and B are the 2-bit vectors, we would first sum up the vector A, we sum up the vector B, and subtract twice the dot product of these 2 vectors. So in these secret sharing protocols, adding secret shared values together and also multiplying by a constant does not require communication. So the only part of this expression here where we have communication is the dot product. So why does this help us? So there exists a class of MPC protocols, most notably this honest majority protocols, which we had before, where Shamir secret sharing is a part, but also replicated sharing protocols like AV3. In these protocols, you can actually compute the dot product with a communication that is independent to the vector size. So in this protocol, it doesn't matter whether you produce a dot product or a normal multiplication, the communication is actually the same. And by using one of these protocols, we can actually reduce the communication significantly. So for the example we had on the previous slide, for 1 million iris codes in a database, we can actually reduce the communication from 3 gigabyte to just 2 megabyte. So this is a huge improvement of a factor of 1,000 already just by evaluating this with the right MPC protocol. So the next part of the computation is then the threshold comparison. And what we realized here as well is that if we have a subtraction here from the Hamming distance to the threshold, If we can ensure that this subtraction does not underflow, then this comparison is actually equivalent to extracting the MSB of this difference. And since our iris codes have 12,800 bits, so so the sum can at most have 14 bits. By choosing integers, 16-bit integers for our shares, we actually ensure that this subtraction cannot underflow, and then we perform an arithmetic to binary conversion to get this significant bit of the difference, and that is how we compute the comparison. So it's basically just one arithmetic to binary conversion. Then finally, if we do not want to leak which iris code was actually matched in a database, we have to aggregate the results of all these comparisons. So for 1 million iris codes, we have 1 million output bits here. We have to aggregate them to one result. And basically, we would want an operation which is 1 if at least one of these results is 1, and we can do this by a OR operation. So that is basically the whole protocol, and if you want to evaluate this efficient MPC, what we need to have is a protocol. Previous slide, dot product that is with the communication independent to the vector size, and there should also be an efficient arithmetic to binary conversion such that we can evaluate this threshold comparison efficiently. And replicate protocols like RB3 are very efficient for this use case because these fulfill both these requirements. Okay, since I said before, MPC protocols, yeah, some problems with the microphone. Thank you. Does it work? Yeah. So since I said before, the main bottleneck in MPC protocols is usually the communication between the parties. So now I want to talk concretely how many bits we have to communicate. So in these replicated sharing protocols, this arithmetic to binary conversion is usually done by evaluating binary addition circuits. And there we can have a binary addition circuit that is either consisting of a lower amount of AND gates, but a higher number of communication rounds. But we could also go vice versa, reducing the communication rounds and increasing the AND gates. But for the low AND version, one such MSB extraction requires 29 AND gates in 15 communication rounds. The other basically just has twice the number of AND gates. So for aggregating all of these output bits into just one, so basically this requires to compute many OR operations, and the OR operations internally have each have one AND gate. So if we have a database size of 1 million, we would have to compute 1 million AND gates. And if we perform this in a binary tree, that the number of communication rounds is logarithmic in the database size. So overall, the whole iris protocol, including the 16 bits communication for the dot product, we have 46 bits of communication per database entry, which is very low in this case. And the communication rounds are 16 plus logarithm of the database size. Okay, now let's talk about concrete protocols and the security models. So we implemented both a semi-honest and a malicious security protocol. The semi-honest version is basically a semi-honest AB3, since this is one of the fastest MPC protocols in this setting, and we will also see in the benchmarks later that the overhead to a plain computation is very small. For malicious security, there exist several different options in the literature to extend this protocol to malicious security. For example, you could use zero knowledge proofs, like in the Swift protocol, to show validity of every AND gate and the multiplication. And we implemented several of those, so I will give you a link for the GitHub repository in the end. And what we realized is actually that it's the best if we use different techniques for the dot product and for the binary computation. So for the dot product, what we actually use is something called speedwise max. So basically, there everybody has a share of a MAC key, a global MAC key, and then if we have a share of our iris bit, this share gets extended with another bit, which is a MAC, which is basically multiplication of this share with the MAC key. So the overhead that we introduce here is basically we have to compute the functions on the share and on the MAC, and in the end we have to compute the MAC check protocol to ensure that this invariant is was correct for all multiplications here. And so this is the overhead introduced, and there's another overhead. Since we are operating over rings, using these MACs requires us to going from a 16-bit shares to 64-bit shares for security. So for the binary world, what we do there is we basically have to compute valid AND triples here. So AND triples are, we have a share of X, share of Y, and a share of the AND combination of those. So, and we have to pre-compute a lot of these triples, and in the end we have a check that where we sacrifice these triples to show that all the AND gates that we had in the protocol were computed correctly. So the overheads here are the pre-computation of the AND triples and the check in the end of the protocol. So then it brings me directly to the benchmarks. So the benchmarks here were performed on 3 different servers located in the same city, so a fast network connection and a database size of 100,000 iris codes, and the benchmarks were single-threaded. The plain computation of the protocol was about 130 milliseconds. So for the semi-honest version of our protocol, you can see the overhead is not even a factor 4. You can see here also the very low communication between the parties of just 0.6 megabytes. And the main overhead here is by the result of sharing each bit as a 16-bit integer. And in the replicated sharing protocols, we have to compute basically everything on 2 shares. In malicious security, the runtime is actually 2.9 seconds and a little bit more computation, and the overhead is, as I said on the previous slide, we have additionally the MACs, we have to compute on 64-bit shares, we have AND triple pre-computation and the triple check. But overall, you can see very low communication sizes, and also, especially for the semi-honest version, a very small overhead in terms of runtime. So now I want to spend a slide talking about why we will not use homomorphic encryption for this use case, and the reason for that is that with everyone we talked about our project here, everybody said, why are you not using homomorphic encryption? And for that, I'm first talking about the security of the MPC solution. So we have a semi-honest version and a malicious secure version. And what we also have with MPC is always we have a non-collusion assumption between the servers. So if they work together, they can recombine the database, which is obviously not good. So we have this non-collusion assumption. Unfortunately, though, when we have homomorphic encryption, we can also not get rid of this non-collusion assumption. And the main reason for that is that we actually want to prevent the server from getting to know the database. So when it has the encrypted version of the database, it must not have access to the decryption key. So there must be at least another party who has the decryption key, and if they work together, they can decrypt the database. So therefore, we also have a non-collusion assumption there. But also, performance is also something where homomorphic encryption is unfortunately not good in this use case. And the reason for that is that from the SAMA DFG library on their website, they already write that the 16-bit integer addition already takes 100 milliseconds. And another thing that we also have to consider is ciphertext expansion. So even when using homomorphic encryption here, the communication size is larger than our MPC solution. And the reason is that when the ORB has an encryption of the iris code and it sends it to the database holder, then this encrypted iris already has 37 megabytes. So this is larger than the communication in our use case here. So unfortunately, homomorphic encryption is not that good in this use case. So let me conclude this presentation. So what we did was we decentralized the iris code database, which is used for authentication in the World ID infrastructure. The problems for performance in MPC here usually the huge database size and the mixed operations, so mixing Boolean with arithmetic operations. But when we carefully design the computation and carefully choose MPC protocol, we can actually get a very manageable overhead. This overhead in the, especially semi-honest version, the overhead was not even a factor of 4. So since a lot of people asked us why not using homomorphic encryption, here homomorphic encryption much worse performance, and also with homomorphic encryption, we cannot get malicious security easily. So if you're interested in what we have been doing, the code is public here on this GitHub link, and there's also a document in there where we describe exactly what we have been doing, and we are also actively working on improvement for this project. So stay tuned and have a look there in the future as well. So thank you for your attention. If we have time for questions, I don't know, then please ask a question. Yeah.
Questions?
Yeah.
Any questions from the audience? Yes.
Just a question on the last side, and I don't mean to offend you by the question. Did you do any security analysis versus TEEs?
Versus these? So yeah, basically we are using MPC protocols for use case, so the security comes directly from the MPC protocols. For trusted execution environments, I'm coming from a research institute where they break these every week. So I would say that we get better security guarantees here. But yeah.
So it's cool that you tried homomorphic encryption, obviously. So I agree with you, right? So we looked at this use case, and if you're using the vanilla operators that we provide in our TFHE library, you're not going to get the best performance for this particular thing. There are ways where you can actually use more low-level FHE crypto to shortcut a bunch of those additions and things like that.
Yeah,
so
sure,
there's quite a big improvement that can be made.
But
so
I think bootstrapping in your system, so I think we would at least have to bootstrap once for each of these comparisons. And the bootstrapping, I think you have better numbers, would be 20 milliseconds or something like that, 10?
Yeah, like 10 milliseconds.
Yeah, 10 milliseconds. So when we do this for 1 million iris codes, then unfortunately that gets too inefficient. So I know there are use cases where homomorphic encryption is significantly better, but I would actually say in this use case, with a lot of optimizations, you cannot get better.
And the second thing also, I might be just interested in case, for the size of the ciphertext, we'll soon be releasing a ciphertext compression system.
Yeah.
So it'll be divided by 10 or so.
Yeah, I think I used that here already. So,
okay.
But I'm not 100% sure.
All right, but good stuff, interesting.
Thanks.
Any other questions? Oh, okay, one last one.
Hello. How do you decentralize it? Like you choose the node operators, or how do you?
So you mean who operates the nodes? Yeah, so that is something that has to be chosen carefully, because if they collude, they can reconstruct the database. But in the end, that is something that a worker needs to do if they want to apply this. But you usually would say they take one server is then maybe someone who is just interested in privacy. There are organizations on that, and ideally a competitor or something like that. So there you need to be careful that those don't collude, but in the end, if that can be managed somehow, then it's okay.
All right. That concludes the, actually, let's thank Roman again